Day 784 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 3739, count subarrays with majority element 2. The difficulty level is hard, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. You are given an integer array nums and an integer target. Return the number of subarrays of nums in which target is the majority element. The majority element of a subarray is the element that appears strictly more than half of the times in that subarray. All right, y'all, so that may seem a little bit confusing at first, so let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. Now, before we get into the examples, let's look at the definition of a subarray. It says a subarray is a contiguous non-empty sequence of elements within an array. So that's just an array of contiguous elements, meaning they're already lined up next to each other. So it's just an array inside an array. Like this would be a subarray. This would be a subarray. This could be a subarray, or this could be a subarray, right? It's just an array inside the array that they gave us. Also want to point out that this has different constraints than yesterday's problem. It might look exactly like yesterday's problem, but this is what has changed down here, these constraints. Now let's go ahead and get into these examples. So in example 1, our input nums equals an array of integers 1, 2, 2, 3, target equals 2. So we want to see how many subarrays we can create with the element 2, where 2 is the majority element. So the output is 5, meaning we can create 5 of those arrays. Explanation says valid subarrays with a target of 2 as the majority element are 1, right? So this right here is a subarray. Boom. Then this right here is another subarray. Sorry, y'all. Right here, that's a subarray. Then this right here is the third subarray. Boom. Then this right here is the fourth subarray. And then this right here is the fifth subarray. And as you can see, all of these subarrays, 2 is the majority element, right? Here, 2 is the majority element. Here, 2 is the majority element. Here, here, and here. They all have 2 as the majority element. Now, just in case that didn't make sense, let's take a look at example 2. So in example 2, our input nums equals an array of integers 1, 1, 1, 1. This time target equals 1. The output is 10. It says all 10 subarrays have the majority element as 1. So in this case, there's no way to create a subarray without 1 being the majority element. And since we have four elements, we know that the maximum amount of subarrays we can create is 10, and all 10 of those will have 1 as the majority element. Now, just in case that didn't make sense, let's take a look at example 2. So in example 2, our input nums equals an array of integers 1, 2, 3, target equals 4, our output is 0. Explanation says target equals 4 does not appear in nums at all, therefore there could not be any subarray where 4 is the majority element, hence the answer is 0. So in this case, target is 4. There are no 4s in this subarray at all, so since there are no 4s, then the output is 0 because there are no subarrays that we can create here where the majority element would be 4. So boom, y'all, now that we understand the question, let's get into the fun part, the actual solution. Solution is not that difficult. Now, first thing we need to do, because of these new constraints that they give us, is we're going to come up here and we're going to create a Fenwick tree, which is a binary index tree, and it's going to support adding a value at an index, which will be big O of log n, and querying a prefix sum in big O of log n. And then in this problem, the tree stores the frequency of previously seen prefix sums so that we can quickly count how many are less than the current prefix sum. So we'll come right here, say final class, call it a Fenwick tree. We'll open up the brackets and we're going to say private var tree colon, that's going to be an array of integers like that. Boom. Now we're going to come underneath this And we're going to say init, initialize, we're going to open up the parentheses, underscore size, colon. One moment, y'all, I'm trying to figure out how I want to do this. We're going to say colon. Oh, sorry, y'all. Boom. This should be an integer. Then we'll come outside of this. We'll open up the brackets. And then the Fenwick tree is going to be the traditionally one index. So we're going to allocate an extra slot. So we'll say tree equals an array, open up the parentheses, repeating colon 0. Hold on, y'all. Sorry, y'all. Colon 0, comma, count, colon, size plus 1. Boom. Then we're going to come underneath this, and we're going to say func update, open up the parentheses, underscore, index, colon, int, comma, underscore, delta, colon, int. Sorry, y'all. Come outside of that, open up the brackets. We're going to declare variable I, set that equal to index. And then we're going to add delta to this position and all Fenwick tree nodes responsible for covering it. So we'll say while I is less than tree.count. We'll open up the brackets and we'll say tree, square bracket I. Come right here, plus equals delta, come underneath, or, sorry y'all, yeah, plus equals delta, come underneath that, and we'll say I plus equals I, and, bitwise and, so 1 and sign minus I. Sorry y'all, oh, let me clean that up, make sure that's right. While I is less than tree dot. Let me see. Boom. That should be right. Let's keep going. Now, come right here. We're going to declare a func called query, parentheses, underscore, index, colon. That's going to be an int. Come outside of that. It's going to return an int. Open up the brackets. And we are going to say declare a variable called I. We'll set that equal to index. Declare a variable called sum. Set that equal to 0. And we're going to accumulate contributions from the Fenwick tree nodes until reaching the root. So we'll say while I is greater than 0, we are going to say sum plus equals tree, square bracket I, come underneath that. We're going to move to the parent node by saying I minus equals I and I, or excuse me, minus I. Boom. Then we'll come underneath this while, and we will say return sum. Boom. Now let's get into our count majority subarrays func down here. So first we need to get nums.count. So we'll say let n equal nums.count. Boom. Now we need to transform the problem. So target will be +1, not target will be -1. For any subarray, sum will be equal to the target minus the non-target, and target is a majority element if target is greater than non-target, which will be equivalent to the sum is greater than 0, and therefore we will only need to count subarrays whose transformed sum is positive. So the prefix sums can range from -n to n, and we're going to shift them by an offset so every index is positive. So we're going to come right here and say let offset equal n plus 1. Come underneath that, we'll say let size equal 2 times n plus 3. Come underneath that, we'll say let bit equal Fenwick tree, parentheses, size. Come underneath that, we'll declare a variable called prefix, set that equal to 0. come underneath that, we need the number of valid subarrays found, so we'll declare a variable called answer, and we'll set that equal to 0 as well. Boom. But we're not done yet, because we need to insert the prefix sum before processing any elements, and this represents the empty prefix and allows us to count subarrays that start at index 0. So we'll come underneath this, and we'll just say bit.update, open up the parentheses, pass in offset, comma 1. Boom. Then we'll come underneath this, and we'll say for num and nums. We'll open up the brackets, and we're going to convert target to +1 and others to -1. So we'll say prefix plus equals, open up the parentheses, num equals target, come outside of that question mark, 1, :, -1. Boom. So if this is true, we'll return 1, else we'll return -1. Boom. Now we're going to shift into the Fenwick tree index space, so we'll come underneath this and we'll say let IDX equal prefix plus offset. Boom. Then we're going to come underneath this, and we're going to say answer plus equals bit.query, open up the parentheses, IDX -1. Boom. Then we're going to record this prefix sum for future subarrays by coming underneath this, and we're going to say bit.update, open up the parentheses, IDX, comma 1. Then we're going to come down here, and we're going to say return answer, y'all. Boom. That should be all she wrote. Let's give it a run. Make sure it runs properly. It's accepted, so let's go ahead and submit it and make sure it's still accepted after we submit it. And look at that, y'all. 24 milliseconds beats 100% of users. That's what I'm talking about. That's what I like to see, y'all. So with that being said, make sure you get one more look at the code. That's the top part. This is the middle part. This is the bottom of the middle. And this is the rest of the code, y'all, in here. With that being said, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.